All right, and we are doing another video, Calculus, Chapter 3, Section 4, and the topic is concavity and the second derivative. All right, so there's two main ideas here. We want to discuss concavity and what it means to say a graph has concavity. And we also want to discuss another test for finding relative extrema using the second derivative. Now, what I want to do first before we start is I want to start with what we know so far, right? So notice I have a table here, a t-table, where on the left I have functions f, f prime, and f double prime, right? So f of x, f prime of x, and f double prime of x. And what I want to do is I want to list in words, right, what each function tells you about your graph, right? What is the information that you get from the function if you give it an x? So let's start with f of x. Now, with f of x, so down here at the bottom of the screen, I have some random x value. If I were to take that x value and plug it into f of x, right? Not a derivative, just f of x. What information would it give you back out? Well, f of x will give you back out the y value associated with that input of x, right? It would tell you the height. It would tell you the y value of the graph at x, right? So that's what f does. So f tells you the y value. Right, the y value at x. Now, what about the derivative? Let's go to the derivative. So f prime of x. What information does f prime give you about the graph if you give it an input of x? All right, so let's go ahead and go back to my x value. So I plug my x value into, now not to my function, I plug it into the derivative of my function. And what does the information tell you about the graph? What do you get back out? Well, the first derivative simply tells you the slope at a given point, right? In other words, it tells you whether your function is increasing or decreasing or constant. Well, let me not say or constant right now. Let's just say it tells you where the graph is increasing or decreasing. Right? That was the point of the last video series. The first derivative gives you some great information about when your function is increasing or decreasing. Why? Because it gives you the slope. And with the slope, if a slope is negative, right? Notice that you have a downward sloping line here, whereas you have an upward sloping line here. Different x values give you different slopes, and that lets you make a statement about increasing or decreasing. And now, what do you think this second derivative would tell you about your graph? That's an interesting question. I mean, the first derivative tells you that you're increasing, but what does the second derivative tell you? Well, again, just in words, the second derivative would tell you the rate of which the slope is increasing or decreasing. With me? It tells you the rate of change of the rate of change. It tells you how fast you're increasing or decreasing. Now that's helpful if you think about it, because if you just tell me something is increasing, right, that doesn't really tell me how fast it's increasing. Like if I were interested in buying a stock, now, and this were the history, let's say the 2-month, 3-month history of the stock price. Now look how, now for sure, this graph is increasing, but the rate that it's increasing is increasing too. Does that make sense? And now here's another graph that's also increasing. Do you see the difference? Both graphs are increasing, but wouldn't you agree with me? It appears that the latter graph is starting to tamper off, right? It's starting to approach some horizontal asymptote or something like that. It's not increasing as fast as it was in the beginning. Whereas the former graph, this again, if we're talking stocks, this would be a good stock to buy. At least it appears to be. Now, so we're going to formalize that on the next page, but that is the gist, right? So let me go ahead and start to formalize some of these ideas. So when we talk about the rate of change of the rate of change, right? When we talk about how fast the slope itself is increasing or decreasing, what we're really talking about is concavity, right? The concavity. So let me go ahead and make sure you understand. Let's take a look at the graph down below. So we're gonna talk about a graph being concave up versus concave down. Right? Now, so concave up, you can see that when your graph is concave up, your slopes themselves are starting to are increasing, right, as x increases. But now look at the graph of concave down. So notice now that your slopes are decreasing. They're decreasing. In other words, you can notice that this is a negative slope here. This is a negative slope here. However, the slope is decreasing as x continues. Let me read the formal definition. So it says, if f is some differentiable function on an interval I, okay, we can make the statement that the graph of that function is concave up on the interval I when your derivative, your first derivative, is increasing on that interval. Okay, so I'm going to highlight that because that's an important statement. We get to say that f is concave up on that interval when your first derivative is increasing on that interval. Let's go back down, follow me back down here. So notice that your derivative is increasing on this interval, right? Look at the slopes. I don't know what the slope of this is, of this tangent line is here, but I know that the slope of this tangent line here is greater, right? You could say that the function lies above the tangent lines is a more formal way of thinking about it. Notice how your tangent lines are below. Okay, so that's what we mean when f is increasing. Your slopes are increasing. And likewise, we get to say that it's concave down on the interval I if your first derivative is decreasing. And that's exactly what we're seeing here. Look at your look at your tangent lines. Look how they are decreasing, right? Or you could say the function lies below the tangent lines. Okay, so now we have an idea of what it is we mean when we say concavity, right? And all I'm going to do at this point is just draw you just a couple concave. This is, now I think I'll do it this way. Ready? So I'm just going to draw some random curve here. All right, and now what we can notice is that at first the graph was concave down, right? Look at what I'm talking about. So concave down would look like this. So notice that in this arbitrary graph, at first your graph was concave down, and then something changed, right? Something changed, and then the graph became concave up for the remainder. So concave up would look, again, something like this. All right, so we have some definitions of concavity. We have some geometric interpretations of concavity. What we want to do now is we want to find out, how do you actually test for concavity, right? If you wanted to say it's concave up or concave down, how could you do it, right? Now it's a little bit easier if somebody produces a graph for you, but how do you do it if you want to do this analytically? Well, the beautiful thing is the second derivative is what's going to tell us this information. Okay? If you can take your second derivative, then you're going to be able to you're going to have the tools to be able to answer questions about concavity. All right, ready? So I'm going to read this theorem, Theorem 3.7, for how you test concavity. And again, let's start with some disclaimers, right? We have to let the function f, we have to let f be a function whose second derivative actually exists on an open interval I, right? So you have to be able to take the second derivative. And now, let's see if we can translate this statement here. If the second derivative is greater than 0 for all x in that interval. Okay, so stay with me here, right? Stay with me. Don't let me lose you yet. What does it mean to say, let me come off right here. This is 1. What does it mean to say f double prime of x is greater than 0? Well, don't you agree with me that's just a positive number? Likewise, the second part of that theorem says if f double prime of x is less than 0. What does it mean to say something is less than 0? It just means that it's a negative number. So, well, okay, let's now assume that you took your second derivative, and let's assume that you plug something into the second derivative. And what pops out? Well, it's possible that what pops out is a negative number, of which case, what can we say? Well, we'll find out in just a second. Or it's possible that what pops out is a positive number, and it's possible that what would come back out would be 0. So hold on. So what can we say in any of these situations? So my apologies here. So if your second derivative is positive, then we get to say that your function is concave up. Ready? So you get a positive number when you plug in something for your second derivative. You now get to make the statement that it's concave up. If you get a negative number, when you plug an x value into your second derivative, you get to make a statement that the function is concave down, right? So now we have now with this behind us, let's jump in and start to answer some questions about concavity. Ready? So as of right now, what we're going to do is we're not going to worry about the first derivative yet. We're simply going to jump in and start seeing how we test for concavity. And now I need you to understand something, that I'm going to take the first derivative and I'm going to take the second derivative without showing the work. Okay? My apologies, my sincere apologies if the ability to take your derivatives is a skill you still need to work on. But please, if at a bare minimum, just follow me through the lecture and then write yourself some notes on things that you need to go back and work on. But right now, just follow the overall concepts, okay? So how are we going to do this? Well, if you want to find the open intervals on which the graph of, I don't think this actually mentions this, determine the open intervals on which the graph of f of x is concave up or concave down. That's the entirety of the question. Okay, so how do we do this? Let's get a playbook going on here. So the second derivative is what tells you this information. So the first thing you're going to want to be able to do is find the second derivative. Okay, that's your first step. So find f double prime of x. Okay, so we're going to need f prime before we can get f double prime. So f prime of x in this case is, let me give myself a little bit of space. So f prime of x, is equal to the following. Negative 12x over x squared plus 3 squared. That's your first derivative. Okay, so just you can use a quotient rule if you would like to go through that. You can write that denominator as x squared plus 3 to the power of negative 1. But however you do it, we are finally at the point where we are right now, where we have the first derivative. Now let's go ahead and let me write the second derivative. All right, so the second derivative of x, now that's a little bit more involving, because you have, well, it's a quotient rule for sure, and then you have chain rules that looks like it's built into this quotient rule as well. So, but when everything's said and done, you would have 36 times x squared minus 1 over x squared plus 3 to the power of 3. All right, I have two derivatives, the first derivative, the second derivative. If I were asking questions about increasing or decreasing, then we would care about the first derivative, but we're asking questions about concavity, so we care about the second derivative. So step 1 is done. Now, step 2 is going to be you're going to find where f double prime of x is equal to 0. My apologies, these little board mistakes. It's hard to talk and write. F double prime of x is equal to 0, or f double prime of x does not exist. Right? That is what we're looking for right now. We're going to look at our second derivative, figure out, does it equal 0? Okay. And what about, are there x values where it does not exist? Let's start with equals 0. And now, if you'll pay attention to me for just a second, I think I can help you here. Let me just write a fraction a over b. Now, do you agree with me that if you want to make this fraction a over b equal 0, then you would have to make a equal 0? All right, if you want to make this fraction not exist, then you would have to make the denominator equal 0. I hope that makes sense. So to ask when does f double prime of x equal 0, we're asking, hey, can you make the numerator equal 0? Can we make this numerator here equal 0? To ask when does the second derivative not exist, we would be asking, can you make the denominator equal 0? Can we make this denominator here equal 0? Okay, so it's okay to have 0 over a number, but we cannot have a constant over 0, right? It's okay to say I want 0 of the 4 slices, but it does not make any sense to say I want 4 of the 0 slices of pizza. So let's jump in. Let's go ahead and do this. So let's start with trying to make f double prime of x equal 0. So okay, so if you followed me through that example, then you know that the only thing we care about is the numerator. If you were just barely listening, then you're going to be saying, hey, professor, what happened to the x squared plus 3 over to the power of 3? That's because you weren't listening. I just said if you want to make a fraction equal 0, make the numerator equal 0. So this is where we are. Now, what x values would cause this to equal 0? Well, you can factor this a little bit more. This would be 36 times x minus 1 times x plus 1, if this is helpful. And what we get back out is we say, look, if I can make this part, this factor or this factor equal 0, then my job is done. So if you choose 1 minus 1 is 0, then the whole left side equals 0. If you choose x is negative 1, then the whole left side is equal to 0. So far I have 1 and negative 1. Let's see if there's anything else. Okay. So now let's talk about when the second derivative would not exist. So remember, now I'm looking at just the denominator. So x squared plus 3 to the power of 3. Can I make that equal 0? Okay, so now if you let me do this. So for many of us, for most of us, we can look at that, right? We can simply look at that x squared plus 3 to the power of 3 and figure out that, look, you're not going to make that equal 0. What could you possibly choose? You can't, right? You would have to make x squared be negative 3. How are you going to make a value squared be a negative number? You can't. If you choose a negative number, you would square the negative and you would still have a positive. So no matter what, x squared is always going to be a positive number. So you're never going to get to 0. But let me do this. Let me talk to that person. Who doesn't, maybe doing math like that in their head has never really been your talent. Okay, but so I'm talking to that person right now, and what I'm telling you is you can still reach this same conclusion. Just solve for x. Okay? Watch what happens. So if I want to solve this equation for x, I would take the cube root of the left side, the cube root of the right side. That would leave me with x squared plus 3 is equal to what? It's equal to 0. All right, let me get rid of these parentheses. They're just cluttering our problem up. So if you take the cube root of something cubed, that inverse operation would be like if I took your age and multiplied by 2 and then divided by 2. So it would cancel itself out. And right now we're still trying to solve for x. So if we subtract 3 from both sides. Now you know what to do. Take the square root of both sides. You get x is plus or minus to the square root of negative 3. Wait a minute. This is a problem. This is a problem if you want to stay in the real number system, okay? If you want to venture into complex numbers, two-dimensional numbers, then that's not a problem. But we are going to stay in the real number system with our calculus for this course. So the square root of a negative number is a nonsensical statement, right? That is the equivalent of if you just think about asking the question of what could you square, what value could be squared, right? This, in other words, what we had right here. What value could you square that would produce a negative 3, right? A nonsensical statement. So, in other words, the only values of x that we're going to use is 1 and negative 1. Okay, so what I'm going to do right now is I'm going to erase all of this little scratch work. Everything except the result. Okay, and then all I'm going to do is just write this underneath it. So for the result from step 2 is what? It is x is equal to plus or minus 1. Okay, so step 2 is done. Now, so for step 3, let's think about how we've been doing this. So remember, if you've lost sight of the overall goal, the goal is, can you find the concavity where it's concave up, concave down? If you're thinking, man, I'm just going to graph this. Well, that is a wonderful technique. In fact, I would use the same technique. But you better hope that the cutoff points, right, the points where the concavity changes, you better hope that those are whole numbers like 1 and negative 1. Because if it's at the square root of 2 over 2, you're not going to be able to spot that from your graph. Okay, so let's take a little bit more pride in our work. Let's actually go the distance here. So what we're going to do for the step 3 is we're going to, just like in the previous videos, we're going to use the fact that when x is equal to plus or minus 1, that your second derivative either is equal to 0 or does not exist. And we're going to use that to do something. Ready? What are we going to do? We're going to chop up our number line. So let's let negative 1 be over here. Let's let positive 1 be over here. And the way you got to think about this is what? Is you start off with this string and you decide to come along with your scissors and make 2 cuts. You make a cut right here at negative 1. You make a cut right here at positive 1. And if you cut a string 2 times, you have what? You have 3 pieces. And why is that important? Because each of these pieces, right? You have a piece here to here. You have a piece here, and you have a piece here onwards. Each of those pieces is either going to be concave up or concave down. I hope intuitively that makes sense, right? I've already read to you. I've already read to you that if f double prime of x is a positive number, then what? Then concave up. And likewise, I read to you that if f double prime of x is a negative number, then it's concave down. So look, what do we know about when x is 1 and negative 1? What do we know about the second derivative? What do we know about here and here? We know that the second derivative is equal to 0. So think about your options. You're either, if you plug in a number into your second derivative, you're either going to get a negative number, a positive number, a zero, or it does not exist. Those are your four options, right? Exhausts your options. So we now know where it's equal to zero or does not exist. So everything else must either be what? It must be a positive or a negative slope. It must mean concave up or concave down. No more talking. No more talking. I just get excited. I can't help myself. Ready? So let's use those x values and let's create some intervals, right? So the first interval was from negative infinity all the way to -1. That's one piece of your string. Remember, you have three pieces of string. The other piece is going to be from -1 to +1. And the last piece of string is going to be from +1 all the way to infinity. And you guessed it, what are we going to do? We're going to find some test point. Right? Some test point, doesn't matter what point it is, as long as it's in this interval. Ready? I'm going to pick -2. -2 is in that interval. And I like 0, so I'm going to pick 0 and I like 2. And now what are we going to do with these test points? Well, you are right. You're going to plug your test point, but plug it where? You have f, you have f prime, you have f double prime. Well, you're going to plug it into your second derivative, right? Because you care about concavity. All right, ready? So what is f double prime of -2? What is f double prime of 0? What is f double prime of +2? And I don't even care what it actually equals. I just care, is it going to be a positive number? Because if it is, I'm going to say concave up. If a negative number comes back out, I'm going to say concave down. And if you plug a -2 into your second, where are you plugging it, right? You're plugging -2 into your second derivative. Your second derivative. You have to plug it into that function. But what would come back out would be a positive number. If you plug 0 into your second derivative, what would come out would be a negative number. If you plug a 2 in, what would come back out would be a positive number. All right. Don't stop, right? Don't stop here. It's like that person who just keeps talking, but they don't ever have a conclusion, right? Say something, make a statement. So if this last part is for you to give me a conclusion. And what is the conclusion? Well, the conclusion is, since it's a positive number, it's concave up. All right, should look like this. I'm going to go ahead and write them, then it should be concave down. Should look like this. And the last one is also concave up. Like this. All right, now let's actually look at our graph and see if our graph bears this out. Ready? So look at the -1, look at the +1. Right, that's the values that we found in the second step. And now look how the graph is concave up. From -infinity all the way till you get to -1, right? And that's exactly the statement that you made. Now, once it gets to -1, then the concavity starts to change. Right now it's concave down. All right, which is exactly what you said it would be. And then finally, when you get to +1, we're back to having concave up. Okay, listen, hats off if you're following me through this, right? It's very easy to trick yourself into saying, oh man, this is easy, I got this, and just dozing off. Do you have this? Well, then you should try one and see if you can produce the result without the graph staring at you. All right, I'll ask one more question. It could be a silly question to some, but it's actually not. What is that the graph of? Is that the graph of f of x, f prime of x, or f double prime of x? That's the graph of f, right? Remember, all of these derivatives that you're taking is so that you can talk about the graph of f. The original function is what we care about. These are just tools. These are tools to make statements about the graph of the original function. All right, so what we're going to do, I'm going to go ahead and take a break, and then when we come back, we're going to you basically at this stage you have the skill set to be able to say where it's concave up or concave down. When we come back, we're going to talk a little bit about the second derivative test, and then I'll show you some applications. See you in a bit.